We're already 5 minutes past the starting time, so I'm going to launch right into it. So yes, I'm Sean Williams, and this is about the programming language that my friend John and I are making. So presumably only a fairly minority of people know what homoiconicity is, so I'm going to devote a lot of this talk to even just defining that term in a fairly precise manner. So I'm going to motivate this with a rather unusual problem. In Haskell, write a function that, given a tuple of arguments that share a type class, maps a function in the type class over the tuple. Now, this is already sort of a test of how well you know Haskell based on how much you think this is a problem. So if we do the obvious thing, this sort of works. So here we're mapping f over the tuple a, b simply by applying f to both a and b. And it works in this case, but once they're different types, then it stops working. So if we, in fact, annotate these as an int and a double, what happens is f has a concrete type, and it unifies f to the type int to int when it encounters fa. So then it encounters fb, and it tries to call an int to int function on a double, and then that's why it says expected int got double. And you may well know that the solution to this is a thing called rank-n types, which allows you to defer this unification of the type variable. So now, if we use this extension and write out an explicit signature where we have to explicitly quantify the type variable, then it actually works perfectly fine, as shown at the bottom. However, now, generalize this over both tuple arity and type class. The first problem is tractable, kind of. You can use functional dependencies to write type classes on tuples that will work out with multiple arities. Probably the saner solution is to go with heterogeneous lists, but heterogeneous lists also perform really poorly because tuples are first-class citizens of Haskell and heterogeneous lists are crazy. So that's still not really a recommended solution. Like, that should not be your go-to answer. As for type class, I think several people cringe because, yes, there are things that you can try. I would not recommend any of them. They pretty much would have to start with constraint kinds and then writing type functions where you map types to type classes. That is just disastrous. Now, on the other hand, this works with no fuss. But you might be thinking, like, what the hell am I doing talking at a functional programming conference if my suggestion is you solve all your problems with writing IDE macros? Well, some people probably predict the next slide. We can use template Haskell. So template Haskell is a GHC extension, and it introduces two new language constructs, which are called quasi-quotation and splicing. Quasi-quote converts code into its formal representation, and splice converts a formal representation, which is a Haskell data structure, into code. To try to make that a little clearer, this square bracket pipe thing is the quasi-quote block in Haskell, and run Q just converts a quasi-quote into an I/O thing. But more importantly, here we can see how this is actually structured. The first element of this tuple is an infix expression, infix E. Nothing means that we're doing the infix closure trick. That is, there is no left operand. And then our second element is the plus variable. And then lastly, we have just literal 1. So it's just because it's maybes on both sides to allow the closure trick on both ends. And then the second thing is the literal 1. Now, you might notice from this, although you probably theoretically know this already, Haskell is based on abstract syntax trees, and this is really showing us the AST of this Haskell code. So given that, we can write code that operates on the AST, and we do that by first binding a number of names equal to the arity of the tuple that we want to operate on. And then we construct the expression that goes in each field of the tuple, and we map it over a tuple. So at least one thing that's good about template Haskell is it lets you treat tuples as lists so that you can then do maps and folds and stuff on tuples. And by doing this, all these cases just work. So the $ parentheses stuff is a splice. So map t returns another quasi-quoted expression, which then gets compiled and injected into that position. So in fact, this becomes literally the code from earlier, where we have a tuple that's just copying and pasting the +1 all over the place. The second example is sort of more interesting. It shows us that we can change the tupularity just by changing the literal we provide there, and we can work on any function. Now, so metaprogramming fundamentally means code generation, but this has taken on a lot of meanings in practice. In particular, type inference is a form of metaprogramming. And we can demonstrate this with yet more parlor tricks that I've seen at least once at this conference. So piano numerals is an early 20th century thing where you define 0 and the successor function. So 0 is just equivalent to the integer natural number 0. And successor is just n+1. Hence, the third successor of 0 is the number 3. So here is Haskell with a whole bunch of extensions. And the important part is this type class in the middle. So we define z, 0, and successor as empty data types. And then we can write a type class that uses functional dependencies and instances the recurrence version of piano arithmetic. So the important thing is I want you to compare the two instance lines at the top to these 2 lines of Prolog code, which is how you implement piano arithmetic in Prolog. The first instance on both cases is actually identical, although you use the number 0 rather than the letter z. And the second line are the same but reversed, which is just a quirk of how Haskell works. So anyway, to try to talk a little bit about this, because this is where this might be going off the rails for a lot of people, I want to talk about both type inference as a metaprogramming system, and expression metaprogramming. So type level metaprogramming, that is sophisticated type inference systems, they're defined by discipline, and that's what everyone really likes about them. And discipline is a good thing. So the bad things that I'm going to say should be tempered by the fact that discipline is still very good. One of the things that kills me about them is they're all about pre-made abstractions. Now, what's good about that is that typically language designers will think long and hard about what abstractions are good ideas, and language users may not devote as much thought to that. But the flip side of that is that if you have pre-made abstractions, then you have lines set for you, and you have to color inside of the lines. And the moment you color even a little bit outside, it gets really, really bad, which was what the tuple example was meant to demonstrate. The in some ways more important and in other ways less important issue is what my friends and I have started calling paradigm locking, which is where you start to become capable only of thinking in terms of existing paradigms, and you miss answers that are even a little bit outside of your paradigms. So that's basically the plot of Thomas Kuhn's Structure of Scientific Revolutions. The reason that happens is because people get locked into paradigms just conceptually and cognitively. There's also a very practical problem, which is that interop to other polymorphic languages is very difficult, because both of them are going to be attempting to metaprogram simultaneously, and metaprograms are run by the compiler, and generally you're not running both compilers simultaneously, so the metaprogramming never really comes together, and that's why it's such a bear to try to do interop between, say, Haskell and C#. And ultimately, the reason that interop in Haskell is almost always to C is because C is a monomorphic language, so it doesn't have any of this baggage. On the other hand, expression-level metaprogramming, the template Haskell stuff, is defined by flexibility. And similarly, you can do user-made abstractions. Of course, the drawback to that is you get an awful lot of rope, way more than enough rope to hang yourself. But on the plus side, you can, if you really want to, you can make an expression-level metaprogrammed language be monomorphic but appear polymorphic. And in that sense, it should solve the interop problem, or rather, it does solve the interop problem. That is, a monomorphic expression metaprogrammed language can interop anywhere. So that is actually one of the most important features to the things that I'll be talking about. So why not both? Well, I alluded to the reason that you shouldn't generally do both earlier. The more that you invest in a sophisticated type system, the more you have to make your expression language complicated in order to compensate for that. And you also typically have to develop syntax that's divided between expressions and type. There's type programming or type specification. And it's very hard to set up a good metaprogramming system that works on a split language. And it's also just very irritating to write metaprogramming code that operates on trees. Trees are not a good fundamental data structure. There's particularly heterogeneous trees. And ultimately, template Haskell does have a problem that it gets very, very difficult to do anything remotely complicated. Now, let's talk about the language that the minority of people who know Homoiconicity were expecting, the great old language Lisp, one of the oldest programming languages that's still in use today. Now, the thing that is really fascinating about Lisp that you may or may not have learned in undergrad, Lisp only has 3 elements in its grammar. Those are symbols, literals, and S expressions. S expressions means syntax expressions. Those are just the parenthesis terminated space delimited lists that we all know and love. Now, you might be asking yourself, aren't I omitting a 4th thing, the list that makes Lisp what it is? In fact, no. Lists are just quasi-quoted S expressions, which is why the way that you write a list in Lisp is to write a single quote, which is the quasi-quote operator, and then an S expression. And because of that, car and cdr, that is head and tail, are both programming and metaprogramming constructs. That is, simply by knowing Lisp, you already know how to metaprogram Lisp. You just didn't realize it. So that is the elegance of Lisp. It's homoiconicity. That's where the syntax and formal language are isomorphic, that is, they have the same shape or same form. That is, the syntax of Lisp is the actual S expression with the parentheses. The formal language is a conceptual version of that. And ultimately, both programming and metaprogramming in Lisp is all about manipulating S expressions. So Lisp is great, but it's interpreted.
No.
Now, I will address that objection later. The problem with an interpreted language is fundamentally that you have to ship an interpreter. So you can always embed an image and an interpreter into a Lisp program that makes your binary size at minimum 20 megabytes. The objection is that, yes, there are Lisp compilation systems. The drawback is that you can never eval non-literals. In order for eval to make sense, you have to contain an interpreter. And in order to be able to handle the dependencies of the interpreted code, you need the entire image. So you will never get away from the fact that the Lisp image has to be embedded in Lisp, or you have to lose out on its greatest feature.
That's an abominable myth. It's no different from any other language. If you need to ship something, if you need to ship an image that can eval, yes, you need something that can do eval. In fact, with any modern compilation system, this will be a compiler, not an interpreter. There is no interpreter present. But even then, you can also ship binaries without an image. There are systems that are quite capable of that.
As long as you don't do runtime eval.
Exactly. Like many programs don't.
Yes. But if your interest is in metaprogramming, then that is kind of a large drawback.
No, but that can all happen in compile time.
Let the speaker continue.
Sorry.
Yes. Because there are more issues. For example, now, people may disagree with me on this, but I do consider dynamic typing a drawback. If nothing else, dynamic typing static typing is a very good debugging tool. And the third thing is it's based on heterogeneous lists, so everything is offset based. That is, everything is car and cdr. So you have to know precisely where things are in order to do anything particularly metaprogramming. So this is mainly to say it's kind of tedious. So we're making a programming language. Yeah. So first off, how do we make things more name-based? That's how do we do away with the problem of only having offsets? One option that we considered was to go from an S expression-based syntax to a record syntax as having a language structured entirely out of JSON. we thought about it. The actual reason that that option doesn't make sense is because there are several operations that are defined by the positions of their arguments. For example, plus. So having to construct mathematical operations out of a very clunky JSON syntax didn't really seem like a very good idea. And having JSON just be a sort of wrapper around S expressions that gets compiled away, that's better, but it would not support heterogeneous cases where you want some named and want some positional arguments. So we actually really took out the shovel and dug up some ancient history. We're doing a stack-based language.
Yay!
So the world in practice has exactly one stack-based language that's still used, and it's called PostScript. So I don't really expect people to.
Factor.
Isn't that
Yeah.
after this talk? Isn't that after this talk?
Possibly, yeah. So anyway, stacks are a bit weird. They're surprisingly elegant. We are doing things to try to beat back some of the stack insanity. So first, what's good about stack-based languages? So probably the biggest thing is you get good support for multiple returns, and particularly composition of multiple returns. So the bottom is showing pushing 8 and 3 on the stack, and then executing div mod from Haskell, the function that returns both the quotient and the remainder of integer division. So that pushes two things on the stack, at which point we can simply add them together. I mean, not that you would ever want to do this line of code, but if you imagine more complicated examples of the same idea. The other thing that people should probably cheer about, postfix notation eliminates parentheses.
No, it's fixed arity that eliminates parentheses. It's fixed arity that eliminates parentheses. You can have prefix notation or infix notation.
Yes. Well, so fixed arity, but that's also, like, you can stretch that a little bit. I mean, I know what you mean. The fundamentals of the language have to be fixed arity. You can actually get away with an awful lot of dynamic arity stuff. You can also do composition of named returns. So how do we do statically typed homoiconicity? In fact, this is the thing that will really put us in the doghouse for this crowd. But one thing that you can do that's actually really cool and sort of interesting is to treat the compiler as a single pass interpreter. And when you're doing that, as long as you statically type all literals, much like interpreters know the types of things as they're interpreting it at that exact point, a compiler that's doing the same thing will know all of the types of all things at the point that it's currently interpreting. Likewise, pointers become dicey, although you could probably include them. They're being excluded for reasons that the previous talk was about. But the big drawback is you have to do aggressive inlining in order to do that, because you have to unroll functions at compile time. Those functions have to be evaluated at compile time. So we do aggressive inlining, which means there's no recursion, because recursion, the compiler has to take all branches of all conditional statements, which means that it would always attempt to unroll recursion fully at compile time, which means the compiler would hit an infinite loop. So given that, no recursion. I do have to say at this point that it's said the reason to learn Lisp is the profound enlightenment experience of finally understanding it. I found that the same is actually true of the all iterative version. You really get to know your problems a lot better in that case. Now, the other thing that I should say at this point is modern functional programming has been demonstrating that higher order functions are broadly more important than recursive functions in terms of the things that people like about functional programming. So a metaprogramming language still gives you access to higher order functions. So presumably this should actually be fine and should even come out looking a lot like a functional language, even though it lacks the big thing that people associate with it.
Could you have just a macro that explains calling a Y Combinator? You have macros, you have higher order functions. This macro explains into calling the Y Combinator onto this non-recursive function. And there you have recursion.
Yeah. Right, just making an abstraction around it. So then the way that you implement it would be interesting. Not to say that you can't, and we will probably look at that option. Really, a lot of these kinds of implementation details are a bit obscured right now because I was racing to get a compiler together in time for the conference, which didn't quite happen. But It's pretty close, and I even writing the compiler has revealed a lot. I mean, if nothing else, I wanted a compiler that was capable of metaprogramming in order to have concrete examples. So at least we're that far. And I do plan on looking at Y Combinator type stuff as an option for macros. The other thing is we do polymorphism as mangle by macro. But by that I mean that polymorphism systems are always based on issuing multiple versions of functions for each concrete assignment of types. So in that, well, okay, almost like, all the prevalent ones, particularly object-oriented systems. I don't know the deep innards.
Doesn't do that. OCaml has a uniform representation for its polymorphic.
Okay. But most languages.
Okay.
Most languages do polymorphism by mangling. So we just have a macro that will mangle functions for you. I don't really want to go into a lot of detail on that, though. I'd rather actually demonstrate some metaprogramming. So the core language provides if, which has this form, which is written out in regular expressions. And because that's probably obscure, I wrote a program below. So what the program does is push hello onto the stack. And then there's an if clause. And see, this is what I mean about fixed arity is not actually a requirement, but because you can always inspect the state of the stack and do things dependent on what's on the stack. So in this case, the way that if works is it takes any number of preceding blocks and it expects a particular form for them. If there is an odd number of blocks, then the last block is the else clause, and then each pair of remaining blocks is a condition body pair. So then the if will push a string onto the stack, and it checks, of course, to make sure that all the branches result in the same stack. So in this case, it will skip over world, push place onto the stack, and then concatenate them, which is, we're just taking plus from Haskell, so that this program will ultimately print out hello place. This is just to show what if looks like, because things will get more bizarre in the next slide. So let's make switch, as in C. So the way that switch works is you have a value, and then you have pairs of a case, a particular value or a candidate value, followed by bodies, and then an optional default clause at the end.
So shouldn't you rename your if into con? So the traditional name for your if is not if but con. You have a laboratory number of case clauses.
I don't really, deal in semantics quite at that. Mainly I'll say if is shorter and it gets the point across. So anyway, we ultimately want to be able to make switch out of if, and we want to do it in user code. So if we convert the switch into an if, then it, of course, looks like this, where we inject val at the beginning of a block that contains the case along with an equal sign, and then maintains the same default clause behavior. So the way this works, so first we need to bind the value that we're switching over to a name, so we generate a name. And remember, stacks work from bottom up, that is, in terms of how the code's presented, or right to left. So if the second item on the stack is a block, that is, if the second last thing that you encountered is a block, then we're in the case where we have a default case at the top of the stack. So we move the top of the stack onto scratch, which is just going to put the else clause aside for a moment. And then as long as the top of the stack is a block, the top of the stack will contain the body of this case, so move it to scratch. And then you fuse the top of the stack, which is the case, along with val, onto a block containing equal sign. So fuse simply does prepending and appending of blocks. And then once you've constructed the block you need, move it to scratch. Then you take the type of the thing at the top of the stack and just set that aside. So then you move all of the blocks from the scratch back to the stack, and then you push a literal of the same type onto the top so that it reorders things so that things will get encountered in the right order. And then you simply push the symbols that you need, the if along with binding the value on the top of the stack to the name val. So this is a little opaque, but it was the simplest example I could come up with that would really demonstrate the power of this. Probably the more important thing to understand is that this is all about compiler dynamics. You metaprogram by understanding how the compiler works. And once you grasp that, everything's golden. One of the biggest things is for us is that stack-based programming promotes point-free style, and it promotes it even more strongly than languages like Haskell do, because you can do so much easier combinator fiddling. And the other broad topic is that homoiconicity lowers the barrier to entry for metaprogramming. It certainly doesn't remove it. It's still quite a bit harder than normal programming, but it makes it achievable, and you probably won't go completely mad doing it. So then I also felt a bit obligated to pose, is it functional? Oh, hold on, I'll just finish this up. So is it functional? I don't know. I'm not very good at categories and definitions. We've done away with recursion. Maybe that's not that big of a deal. I've come to see functional programming as a design aesthetic, and in that sense, it certainly has that. We do have the other property that I consider very important, which is referential transparency. Stacks actually get quite a bit of referential transparency to start with, as long as you implement dupe as a deep copy. So at the very least, I would argue a language that is referentially transparent and promotes point-free style and higher order functions is probably still pretty functional. So yes, that is the end of my talk. So I know there was sorry.
My question was the macro-based moving things into scratch, as you call it. Can you talk about if there's any correspondence between that and sort of the creed does immediately that exists in Forth?
You know, I never actually learned Forth.
Oh.
Yeah. But the scratch is meant to replicate the the traditional stack. That is the stack. If I just say the stack, the one that you think of, the one that stack frames and that you use when calling functions, because in principle that should be a recursive algorithm, but it's not. So because it's not a recursive algorithm, you have to have an explicit stack. So I've been finding that it's adequate to have the compiler simply provide a fairly generic scratch space that can take tokens and blocks and just push them for later consumption. Yeah, so it's really more like that. Yeah.
Are you familiar with the programming language Joy? And if so, can you describe what differentiates Rio from Joy?
I don't. What's it like?
Joy is a concatenative language.
Okay. So
much like Rio.
Trying to extend that, also, I was wondering if you looked at cat. Because it sort of adds more static typing into Joy, but it's a direct extension of it.
Okay. So I did look at Kitten.
Oh, right, which is like a remake of cat.
Okay. Yeah, the big difference between those is, at least from what I saw of Kitten, which I can't speak for Cat or Joy, there wasn't the metaprogramming focus. The concatenative style is fantastic, but but we really did want a very heavy expression level metaprogramming language where it's tractable, and that is the focus. Hence, that's why it's in the title rather than just this is a stack-based language.
Well, because Forth and Factor both have pretty strong metaprogramming support.
Right, and they're dynamically typed and interpreted. Yeah.
Well,
Right. It's always sort of. But because Rio is doing this massive compile time, unroll everything, that is the answer to the embedding the interpreter problem.
well, this is what Stalin does as well.
Mhm.
It's a scheme compiler that is extremely efficient. It's the same idea.
You're right. So to my knowledge, all of these things are out there. I don't want to say that we're doing something just unique, right? Almost everything in this, except for the content of the previous talk, I've encountered before, but I've never seen them all come together at the same time. Any other questions?